So in today's series of lectures, we're going to be looking at parsing. So what is parsing? Well, in essence, it's the opposite of the problem that we looked at in the previous series of lectures. In the previous series, we looked at manipulating data type descriptions, for example, to print them out. In this series of lectures, we're going to be looking at going in the other direction, taking unstructured data in the form of strings and converting them into structured data such as recursive data types. And so, as we saw before, these kind of expressions, and we use the examples of arithmetic expressions, can be modeled as data types. And we've seen how to go from, for example, expressions to strings using this show expression. And now we're considering how we might go in the other direction. Now there are a bunch of functions. There's a standard type class called read, which contains functions for converting strings into various things. And these work for predefined, a small number of predefined types, but they don't work for arbitrary data types that we define. So we don't get any parsers for free. So this, of course, is a well-known problem in computer science and a very important one. Typically when dealing with programming languages, but it also, of course, the terminology comes from the study of natural languages and creating and understanding the components of a natural language, breaking down the components of a natural language sentence into its constituents of nouns and verbs and so on, is also known as the process of parsing. Now we're not studying it for its own sake. We're not studying parsing because parsing is somehow a central topic of the course. But it turns out that it's a very good way of exercising a whole load of functional programming goodies. Okay, so let's imagine that we're not going to try and convert strings representing arithmetic expressions into this data type. But let's suppose we're actually working with a much smaller data type. How might we do that? And when we do this, we need to keep in mind that we want to parse real expressions. So, for example, if we want to parse numbers, we might think that we would like a function from strings to int, so that if we take a string containing a number, a couple of numerical characters, digit characters I should say, then the number parser, we would hope that converts it to 23. But what should happen when we apply this parser to something which is not a representation of a number, or maybe more interestingly, something which starts with a number and continues with something else? So when we're parsing a string, taking a string and converting it to a number, there are essentially three cases to consider represented by these three examples. Firstly, the string is already a number. The second case is when the string is simply not a number at all. And the third case is when the string starts with a number. Now, cases 1 and 3 are essentially similar. You can think of case 1 as being a special case of case 3. So the way that we're going to represent this, a natural way to do this, to represent the possible outcomes of these three kinds of parsers, is to use the following type. If we want to create a parser for some type x, in this example it was int, then we want a parser to be a function which takes a string as an input and maybe gives us a thing and a string. We use the maybe type because a parser can sometimes fail. We don't want to throw an error, we want to give a value that represents a parsing failure. And that's because sometimes we have to try and parse something, and if we fail, we have to try to parse it as a different thing. That happens when we have choices in our language. So if the parser fails, what we want to do is return nothing. And if the parser succeeds, we want to return a pair of things, namely the thing that we found and the rest of the string. And the reason we want to do that is because often we want to parse one thing followed by another. So once we've parsed the first thing, we now need to look at the rest of the string to do the rest of the parsing job. And that's why we want to return a pair of things, the unused input being the second one. So this is an important idea, that a parser for a thing is a function from strings to maybe a thing and a string, to paraphrase or plagiarize Cat in the Hat. So if we want to parse numbers, we have a string and we want to extract the number that is represented in that string, then we have indeed these three cases. If the string is a number, then what we should get as a result is just the number and the empty string, indicating that there's nothing else to do. If the string is not a number at all, we should get nothing. And if the string starts with a number, we should get the number together with the rest of the string. So this idea will be the core idea for defining and working with parsers. Now, the reason we're looking at this example, as I say, this is not a course in parsing or language technology, but it's a great example of the use of higher order functions, the use of abstract data types, and we'll talk a little bit more about that later, and also the use of monads. So monads here, if you remember, monad is the type class that contains IO and also gen. They're the things that we can build using, for example, do notation. And we'll actually see how we can write a parsing library, which will be an instance of the class monad. So we'll actually be generating our own little instructions for parsing. And we'll see how that works as part of this series of lectures. So in summary then, we're going to break this down into 3 parts. Part 0 is to do with nitty-gritty details. Given that we now understand what the type of a parser should be, let's actually write a parser for a very small expression language. It's going to be quick and ugly. We're going to get the job done using this idea of functions from strings to maybe a thing and a string. But it won't be terribly reusable. We're going to write a specific parser for a specific language. In the next part, we're going to look at a library, that is to say a module that we've defined for defining parsers. So this is a reusable library of components we can use to write any parser. And the core ingredients of this library will be that we'll represent a parser as an abstract data type, an object in an abstract data type. So an abstract data type here is, you can think of it as a hidden data type, a data type whose constructors are hidden. So we don't know really how it's actually represented, but all we can do is work with it and the functions that are provided by the library. And this is very much how we worked with gen. We don't know what the constructors are of the gen type. We simply know how to build gens using library functions, how to build generators using library functions, and how to compose them, in particular using do notation. And the same story will apply here. We're going to see how we can build parsers using the functions from a library. And a key function from this library is, given a parser, we need to be able to actually run the parser. So we need a function which, given a parser, can run the parser, namely, given a string to parse, will actually do the job. So a parser from an A is a function from strings to maybe a thing and a string. Okay, so that's the plan for the second lecture in this series. And finally, relating to the second lectures of this week, we're going to look inside the parsing library. How does it actually work? We're going to see, for the first time, how to make our own first homegrown monad. How do you make something an instance of the type class monad? And in doing so, we will actually give an introduction to monads. So these 3 stages in this development serve very different purposes. The third stage here, looking inside the parser library, is exercising both higher order functions to the extreme and learning about monads. The parsing library itself is something that can be understood independently of how it works. And this is something you'll need if you do the standard Lab 4. So the standard Lab 4, you will need to use this library to build a parser for a similar language of expressions to the ones that we use in the examples. Okay, but before we go on and leave you to move on to the very first of these, which is basically understanding from first principles how you write a small parser, I want to say a couple of words about grammars. So this is a general computer science concept that many of you will have seen before, but if you haven't, it's not too difficult to pick up the basic idea. So a grammar is a standard way of defining a language, and this is something that has turned out to be more successful in computer science than its origins in linguistics. But we're going to use this, occasionally refer to something that's sometimes called the EBNF grammar format. And this has nothing to do with Haskell, this is general computer science. So here is a grammar for representing expressions in a very small language for writing numbers and addition of numbers. And so we define various syntactic categories. Digits are any one of these things. Numbers is a digit followed by 0 or more digits. So that's what this brackets, curly brackets, means, 0 or more digits. And addition is a number followed by the plus symbol followed by another number. So the quotes here are nothing to do with Haskell quotes. These are just quoting literals in the EBNF formalism. So intuitively, this should I mean, it does look a bit like Haskell because we use this alternative bars to represent one, individual things, and you can use recursion, but this one has not used recursion; it's used iteration. So we could have said a number is a digit or a digit followed by a number. We could have given a recursive specification, but here we've used iteration, 0 or more, as the specification for numbers. And so basically the basic concepts in these grammars consists of alternatives, sequencing, and 0 or more things. Okay, so that was just a summary of something that we will come across occasionally in the lectures. We will use these kind of grammars to motivate the structure of our parsers. This one is a slight refinement of the previous one because numbers shouldn't start with a 0. So this one is specifying things which don't start with it. So a number is a non-zero digit followed by 0 or more digits. So the non-zero digits are these ones. And a digit is a 0 followed by a 0 or a non-zero digit. Anyway, hopefully you get the idea. This is not such a big deal, actually. Okay, so there's the plan. The first step in this will be to define a parser. There's a type synonym for a parser. A parser function for an A is a function from a string to maybe a thing and a string. And let's see how this works in action.